Okay, it always is surprising. Hi, everyone. Today's lecture is on graph representations. And just a reminder, the project sign up was finished and I made a schedule, and we had to schedule some outside of lecture time because there weren't enough slots. So please let me know, please look at the schedule and let me know if it doesn't work for you, and then we can try to swap the slots or figure out something. You can make a post on EdSTEM. And also please sign up for your project if you haven't already. So like I know people sign up for their groups, but if you haven't chosen a topic, please do so as soon as possible. Thank you.
How long was the presentation?
15 minutes. Thank you.
Are they going to the final grade? Or
Sorry?
are they go to the final grade, like the presentation for the proposal?
Yes.
Okay.
It's in the syllabus, but the presentation is 9 points and the write-up is also 9. Thank you. Okay, so we will do graph representations, which is exciting because I really like this topic. So just to recap, we talked about this previously when we were talking about graph optimization, but there are many ways that you can represent a graph. Graph is this abstraction with vertices and edges, and the vertices are connected with edges, and they can have some meaning like friendship in a social network or connections or things like that. So the most traditional way to store a graph is in adjacency matrix. And for adjacency matrix, you have a n by n matrix. In the unweighted case, it's a Boolean matrix, and each row and column is corresponding to one vertex. So you have, if you have n vertices and if you have n vertices, then each row, like you have n rows and n columns, and you have a 1 if the edge exists. So a row, so a connection from U to V, and a 0 otherwise. And because most graphs in practice are sparse, people, rather than storing the edges implicitly, like an adjacency matrix, which is independent of the size. So the adjacency matrix is independent of the size of the graph. It is n squared no matter what. But however, if you have many fewer than n squared edges, it sometimes is better to explicitly write down the edges. And the most easy way to do that is an edge list. So an edge list in the unweighted case, you just write tuples representing the edges. So like here, you have an edge from 0 to 1, and then here you would write 0, 1, and then so on, all the way down. And this is the edge list corresponding to the adjacency matrix. And the edge list takes size proportional to the number of edges you actually have, whereas the adjacency matrix is fixed no matter what. Another way to write the edges explicitly is an adjacency list. So rather than just storing like a list of the tuples, you can also store an array of pointers. And in this way, you can avoid writing the source repeatedly. So in edge list, you have to keep writing the source every time. But if you have multiple edges with the same source, you can just basically make them a linked list. And you just write the destination in each entry of the linked list. So here, like the source is implicit. You have an array equal to the number of nodes you have, and then each entry in the array has a linked list, and all of the things in the linked list are the adjacent edges, are the adjacent vertices to that vertex, where the ID is implicit. So like vertex 0 would have neighbors 7, 5, 2, 1, and 6 in this example. And you can basically linearize those adjacency lists, those linked lists, into contiguous arrays, and that would give you something called compressed sparse row, which is the classical format for storing graphs. And compressed sparse row, we've talked about this before, has two, in the unweighted case, has two arrays. The first one is offsets, which tells you the index at which that vertices neighbors start. In the edges array, which just stores the edges in a linearized way, like it stores the contiguous neighbors of every vertex one after the other. So the vertices of neighbors zero, or sorry, the neighbors of vertex 0, then the neighbors of vertex 1, and so on until the end. And then the offsets is the index into it, and the last item in offsets is the total number of edges you have. Is this all good? People remember this? Great. All right, so yeah, so we went through these basic representations: adjacency matrix, edge list, adjacency list, and compressed sparse row. What is the space usage for those representations?
If you got a square for the adjacency matrix, then 2n for the edge list probably. No, and that's yes.
You can do in big O. Oh, Ben?
Yeah.
Yes.
List.
Mhm.
Basically the same thing.
N plus n. You have one cell per vertex.
Oh, yeah.
We have one thing in the linked list per edge. Why is n plus n?
The original, like, the offsets would be like n for each vertex, and get all the edges.
Yes, exactly. So like you said, GCD matrix is n squared, edge list is m, and then GCD list and CSR are both m plus n. So this is just in the big O. What about the cost to add and delete edges in the representations? You don't have to keep them in order in the edge list or the adjacency list, or like maybe you can give two bounds, one for keeping them in order and one for not. They may be different.
Basic matrix we just go for
Mhm.
edge list, I mean, like, yeah, edge list and adjacency list would all be O1. If you want, I guess, if you want to keep them sorted, it'd be like log n something. No, this is space, sorry.
No, this is time.
Oh, time?
Yeah.
Oh, yeah, then, yeah, it'd be log n.
Why is it login?
I mean, you said like upper bound to keep it sorted, so like. You have to do some sort of like binary search. And then,
But then what about the cost of shifting the stuff?
so yeah, upper bound then is O of m. Then for CSR. I mean, I assume that it'd be O of m, because you stuff you have to shift like, different combination offsets.
Of m.
Yeah.
So you have to, you have to shift the edges, but what about the top?
You just change, I mean,
How many do you have to change?
we have n offsets, you have to change a lot.
You have to change potentially all the offsets, and then you also have to change, like, if you put it in the front, you have to shift all the stuff down.
Would we allow like blank spaces in CSR?
If you allow blank spaces in the CSR representation, it may be O of m, but where would you put the blank space? Well, actually, I will talk about a representation later where you use blank spaces, but it is actually non-trivial to know where you should put them to prove some bound. Because like if you put them arbitrarily, in the worst case, you can force like O of m, like in an adversarial case. Good. Yes. So like you said, in a GCC matrix, it's O1 to modify it. In edge list, it's O1 to add it because you put it at the end. To delete the edge, to delete the edge, you have to shift them all back up. This is just assuming that they're all kept contiguously in memory, so you have to shift them all back to fill the space. For adjacency list, depending on whether or not you allow duplicates, it can be also possibly ordered degree. Like if you don't allow duplicates, you have to look through the whole thing to see if it's already there. Otherwise, it's O1 if you can just put it at the end. To delete the edge, it's degree because you have to look through the whole thing. And compressed express row, we just talked about it. It's m plus n because you have to shift both the edges and the offsets. Okay. And last, what about the cost to find all the neighbors of the given vertex? Like given a vertex V, I want to iterate over the neighbors. This was something that we, like last time we were talking about BFS and algorithms, and you have to do this a lot in algorithms.
Do we need to traverse neighbor to count it as like found, or do we need just like a space? Or
Not
like
necessarily.
memory location where they start and basically.
So this is like a different, the first one is iterating over the neighbors.
Yeah.
And the second one is just finding, like returning true if W is a neighbor of V. So those are two different operations. Yeah, so we'll do the first one first, like iterate over the neighbors, not find the endpoints.
The matrix is open on, because we know the index of the vertex, right? So we get directly all the neighbors. But if we want to iterate to them, then of course it's degree of the vertex.
O of n, right, in a matrix.
Yeah.
Like, how do you know where the neighbors are?
Oh, I see. I thought just like a.
Yeah, sorry. So you want to like,
Yeah,
you give a vertex V
yeah,
and you want to
Yeah, that
return all the neighbors. Yeah, so yeah, for GCD matrix is O of n, but for edge list. O of M.
Mm,
You can assume that the edge list is sorted.
and
I guess if you want to find the front, well, if you assume that it's
Okay.
not sorted, it would be O of M, and if you assume that it is sorted, you could do log of M.
Yeah.
Degree or
Yeah. Mhm. Yeah, for adjacency list. Degree of B, and then same for CSR, because you just follow the offset.
Yeah.
Okay. Yeah, so I guess this is in the unsorted case, it would be all of them. The last one is you want to find the neighbor, like just tell, like this is different, this is iterate over all the neighbors, and this is tell me if W is a neighbor of B.
so void, edge list would be O of M. Adjacent list would be like O of degree B.
Mhm.
CSR would also be O of degree.
Good. Yes, so exactly O of 1 in the matrix, O of M in the edge list, assuming unsorted, degree of V in these. If this is sorted, I guess you can also do this in log of degree of V, because you could do like a binary search in the range.
Edge list?
The CSR,
Oh, yeah.
yeah, you see what I'm saying? Like if that subsection is sorted, you can just do a binary search because you have the endpoints. Okay, good. So this is, yeah, this is some bounds for these basic graph representations. And you can notice one important thing is that there's this tension between adding the edges and finding all the, so you want to do both of these ideally in dynamic graphs. You want to add edges and you also want to run algorithms. So you want to find, like last time we did BFS, and one basic subroutine is that you have to find all the neighbors of a given vertex. And what you can see, like in adjacency matrix, you have the best case for adding edges, but you have in some sense the worst case for finding all the neighbors. Now, on the other side, you have like the worst case for adding the edge, and then you have the best case for finding all the neighbors. So for the case, if your graph is dynamic, neither of these is really clearly the best option. Like you have to pay one for the other. So remember, I said something like this in the beginning of class, but there's two main kinds of locality. The first one is spatial locality, which is how many accesses your algorithm makes to nearby data over a short time. So you can think of spatial locality as like optimizing for cache lines. And there's temporal locality, which is how many, over time, how many repeated accesses are you making to the same data? So that's more of like a cache hierarchy thing, like taking advantage of stuff like L1, L2, and so on. Whereas this spatial locality is in some sense independent of the levels of cache. It's only dependent on the size of your cache line and how fast it can move through the hierarchy. So which type are we interested in targeting for graph optimization in general? What?
You know what guys you want from what the travelers being able to.
Good. Yes, exactly. So like you said, the basic operation that you want to do is you want to iterate through the vertices. So this is the BFS example that we did last time. The main operation is like you have this queue and you want to dequeue it and such, but the main operation is for all the edges in the neighbors, you have to do some processing on it. And for in the BFS case, you only do every neighbor list exactly once, or at most once. But you may have other examples, like in triangle counting. The most basic way to implement triangle counting is you iterate over all the edges that you have. You do like a two-finger intersection, basically, in CSR. Like triangle, so edge triangles are like you have UV, VW, and like VWU, like that. And you want to count how many you have. So the most basic way you would do it is like you have one that shares already, like you look for edges that already share one endpoint and you see if they share another one. And then the way you can do that is if the neighbor list was sorted, you could do like a two-finger scan, and then you would just increment every time you see a shared neighbor. And again, that is a scan. And in this case, you may iterate more than once over a neighbor list, but you don't know if you will upfront. Like without knowing the algorithm, you don't know if, in this case, you maybe have temporal locality, but like in arbitrary cases, like in BFS, you don't. So you would optimize for spatial locality. So the main problem in graph representations is, can we choose data structures to support both efficient scans and updates? And even in these basic cases, like adjacency matrix and CSR, you see this tension between scan and update. Those are like the two far extremes. In arrays, you can do really fast algorithms, but you cannot update it. And in adjacency matrix, you can update it super fast, but doing the algorithms is hard because you have to iterate over the entire row. Questions? Does that make sense? Yes. Yeah.
Where does adjacency list fit in?
Adjacency list, I would say the update performance is like somewhere in the middle. Like the query performance is not as good as CSR because it's linked list rather than array, but the update performance is not as good as adjacency matrix because it's like either order. It's setting a bit is faster than swinging the pointer, even though both are order 1. And in the worst case, in adjacency list, you have to do order degree, which is omega of order 1. Big omega. Yeah, so it would be like somewhere here, maybe.
They are probably not even like on like the actual Pareto frontier of like this graph.
Who is the adjacency list?
Yeah, it- or
It can be, like, it's not worse in both dimensions than either of these. So, yeah, does it probably make sense? So it turns out that there's been like 30 years of papers in this area, but we will go through a few. So this is like one of the older ones. You can see it's from 2012, which now is over 10 years ago, but it's a good example. So this one is called Stinger, which is a high performance data structure for streaming graphs. Actually, I think it came from Georgia Tech like 12 years ago now. So that's fun. Yeah, so the high level design is that it is based on linked lists of blocks. So it's kind of like adjacency list, but rather than having one edge per linked list node, you just kind of like coalesce the nodes into blocks like you would in a B tree, but instead it's a linked list. So edges incident to the given vertex are in this block linked list. And so, for example, like you would have the neighbors of vertex 0 are 3, 5, 6, 7, 11, and 20. And block linked lists improve the locality compared to the regular adjacency list because you have more spatial locality. You get more elements per cache miss. One of the things that they introduced or that they studied in Stinger, not necessarily introduced, is something called batch updates, which is rather than like in regular data structures, you think of the API as either like insert or delete one element at a time. And you can also concurrently, like in the concurrent world, we were doing concurrent data structures a while ago. Those are still based on point insert and delete. You're just doing them all concurrently. But batch update is like a different API where rather than doing insert 1, you have something like multi-insert and you pass it an array of things that you want to add or delete. And yeah, so this is like a picture. You have a graph, you have a bunch of edges that you want to add, and then you populate them all into the graph. And this is one atomic operation on your data structure. And batch updates are way easier than concurrent updates because you don't have to deal with synchronization. Like basically you have the entire data structure to yourself to apply all these updates. So you can parallelize between these updates, and you can do specific algorithmic tricks to apply the updates. Whereas in concurrent updates, like you didn't have enough parallelism to parallelize within every single update. There's only about log n work inside, so it's not worth it to do the parallelization inside. And you can also, not really from a theoretical standpoint, but from a practical standpoint, you can often reduce the overall work of every update in the batch case because some of them the high level intuition is like some of them may share work. Like if they share search paths that they have to go down, then you only have to do that once per group that has to touch that area. So this is not a theoretical thing. I think that's more of a practical thing, but the update parallelism is a theoretical thing also. In addition to a practical thing, you can get pretty good scaling. So this is just a small illustration of how you do the batch update. Suppose you have this graph and you have this batch of edges. So 0, 1, 2, 3, 3, 8. And in Stinger, the easiest way that they do it is you can just trivially parallelize over the vertices. You just, all the linked lists are separate and you just add into them. And these are the plots that they had in their paper. They are adding a bunch of edges in batches of 100K at a time. And they have these 3 different machines, Intel Xeon, Cray XMT2, and Cray XMT. The circle one is Intel Xeon. Oh yeah, y-axis is updates per second, up is should. X-axis is number of processors. And yeah, you can see that it scales pretty well with number of threads, but not amazingly. Like maybe this is 100K and maybe this is, yeah, so this is like 15x, but you have way more than 15 threads. So it scales okay, but not great. And then these are even worse down here.
Are the graphs like random or real world?
In this case, they generated them from an RMAT distribution, which is a skewed distribution. So it is synthetic, but it's not uniform random. Make sense? Yeah, so as you note, one of the main problems I think is that they don't, like a lot of the edges may go to one node and they don't parallelize efficiently in a single vertex. Like they can trivially parallelize across the vertices. But if you want to parallelize inside one vertex, that becomes harder. You need like special algorithms. Or you could use like a concurrent linked list inside, but you need to do something more complicated.
Yeah, also I think real world graphs also have like,
Yeah, they are also like non-uniform.
Yeah.
Mhm. Yeah, so this is it's a drawback of this thing, but again, this is like 12 years old. So it's a good first step. And I did some more experiments. So y-axis again is updates per second, x-axis is number of processors, and here they only did it on this Cray XMT. I think this is maybe the machine with the most memory. I think. Not sure why they picked this one, but they vary the batch size. So previously they had fixed the batch size but varied the machine. Now they vary the batch size, and at a high level, the bigger batch size you get, the better scaling you get, which kind of makes sense because you get more parallelism over across the edges. Questions? Okay, so we can move on. Yes, go ahead.
for that side, how are they generating the edges to add?
They generate from RMAT. So RMAT is like a recursive graph. It's like a synthetic graph generator. So they generate a bunch of edges with RMAT and then they cut it up into, like you, for example, they could generate, I'm gonna make up a number, 5 million edges. Then they would cut up those 5 million into sections of like 100K for this experiment. You would just like pick the first 100K and add them, and then pick the next 100K. Huh?
Edges are uniform.
The edges are in a skewed distribution. In a skewed distribution. RMAT is it's like a recursive thing. Basically, you can think of it like the way it works is that you take the adjacency matrix and you cut it into quadrants, and then you set probabilities of how much you'll generate the edges in the different quadrants. You know what I'm saying? And then if the probabilities are not equal, then it is skewed because you would, like, suppose you set the upper left quadrant probability higher, and then and it's recursive, so you keep cutting into quadrants like that. Make sense? Yes.
So, I mean, in these graphs, you always see like after like 64, it kind of just stops scaling.
Mhm.
Is that just like due to their algorithm or like?
That's probably due to memory bandwidth. Yeah. Usually these things are memory bandwidth bound. Good. Okay. All right, so let's keep going. So there were papers between 2012 and this one, but I thought this one was interesting. So yes,
Yeah, sorry.
let's go back a little.
So if it's like a battery, power, right, why is like for 1 million batch size, it's still scales and for the other one?
Because you probably have more locality in the bigger batch size also.
Mhm.
Like more edges are going to the same nodes.
Okay.
Question. Okay. So yeah, so that was Stinger, and at a high level, like you can usually trivially parallelize over the vertices in these things, but it is harder to parallelize over the like one level down. So in this one, they do parallelize one level down in trees. And I'll tell you how they do it. So the way this works is that this one, they use compressed purely functional trees. And purely functional means like a programming paradigm, but functional means that they preserve, instead of like writing, traditionally, when you write a data structure, you just write over it in place, like you have one copy of it and you just keep modifying it. Here, they don't have one copy of it. Every time you want to modify it, you have to do some copying, and that allows you to do versioning. So it preserves, every time you update it, you preserve a previous version by doing path copying. It's not necessary in the data structure. This is like orthogonal to the data structure. Like a tree can be in place or functional, but they happen to do it in a functional way here. And at a high level, they introduce these things called C trees, which are, they're basically, in my view, kind of like, they're basically like, you can think of it, you cut up the array. I mean, they tell you how to do it in a paper, but you take the entire like sorted list of what you're trying to store, you flip coins, and then the things that won the coin flip get promoted, and then you build a binary tree on the things that got promoted. That make sense? So this is like a traditional tree, just a regular binary tree, and this is a C tree. So here, the things that won, this is the set of things that you're trying to store is just the numbers 0 through 6 or 0 through 7. And here, the things that in the C tree, the things that won the coin flip are 2, 5, and 7. So those become the heads of your tree, that you build a binary tree on them, and the rest of them are just stored in contiguous arrays. So that part is a little bit like B trees, but in B trees, all the elements are at the bottom, and the fan out is B, and here the fan out is 2. Okay, so what is the expected height of this thing in terms of the number of elements n and the promotion probability B? Yes. Yeah, because they're n over, in expectation, you have n over B heads, and then you build the tree. Good. Yes. Why are they doing this? Why are we making the tree? To store edges in it. Like any data structure can be used as a graph data structure if you just add the thing one level up. Like you have like the offsets in CSR, you can generalize that to a pointer array. And then in the dynamic case, the pointer array can point to any, like the easiest way to do it, like you make an array of size n and then you point to like STD set, for example, or unordered set or anything. So this is a replacement for STD set. Yes.
Can you repeat how exactly we like derive what edges do we have from the C tree? So I got that we flip a coin and then we take the nodes and then we make them heads.
Mhm.
So but how do we map like the 3, 4, 6, 0, 1 to like the initial structure of the tree that we had, or we don't?
What do you mean the initial structure? Oh, this thing?
Yeah.
You don't.
Oh,
These are, sorry, these are totally independent.
Right.
This is how you just build a regular functional binary tree. Thank you. Yes. This is, I think they build this from the array rather than from a tree.
So then like each node in the C tree also has a prefix array.
So the entire C tree has a prefix, which is the stuff before the first thing that got promoted.
Okay, so like we have 2 and its prefix is 0 and
Yes, but not every node has a, well,
no, but like 5's prefix is 4 and 3, or am I not understanding this correctly?
yeah, I think, they just call it like the suffix rather than, like they think of it rather than this, like they think of everything in the tree as having a suffix, and then they just think of the whole tree having one prefix, which is the stuff that came before the first promoted element.
Okay,
You could also think of
3,
it,
4 is not a suffix or a prefix of 3.
3, 4 is a suffix of 2.
yes.
Yeah, we have a node. So
Yes, so here, like they think of the nodes having suffixes and the entire tree has a prefix. You could also say the
yeah,
entire
okay.
tree has, you could also say every node has a prefix and then the entire tree has a suffix.
Yeah.
Because you have the stuff at the end.
Like TLDR, we're reading from left to right.
Yeah, like if you wanted to read all the edges, you would just read the prefix left to right, and then you would read like every node left to right. And
It's being promoted. Or just?
6 is not, 5 is promoted.
Then why we put 6 as the?
Because it's 5 suffix. Because we discussed
Yes.
node as a suffix.
So 2, 5, and 7 got promoted, and then you build a binary tree on the things that got promoted.
Oh, I see.
And then like the things that come after that are just like the stuff between the promoted stuff.
We're just randomly cutting up the array into blocks and then we build a user tree with the representative block.
Exactly, yeah, exactly. Yeah. Okay. So why are we having C trees when we already have B trees? And the reason that the reason that they say in their paper is the problem with B trees is in a purely functional setting, when you want to do this like path copying, the C tree, you only need to path copy the like root to leaf paths. And so in a B tree, the root to leaf, every node has size B. And so the copying can be very large in aggregate when you look at the entire tree. But in C trees, you only need to copy the heads of every node. So you don't need to copy the suffix except at the bottom, which is the thing that actually gets updated. And you also have to copy, you also have to copy the pointers. So you save the pointer copying by using fan out 2 rather than fan out B. Pretty much. Yeah. But in an in-place setting, I think you would just always prefer B trees. Because B trees have better theoretical bounds, and if you don't care about path copying, you might as well use the fan out B.
Yeah, I think I have a lot. First of all, like, why do we need path, like, what settings?
So functional data structures don't ever actually, like normally when you have data structures, you just like write to the node that you want to update.
Okay, because we make copies, so.
Yeah, because you make copies, like you always have like past versions of the data structure.
So every update basically covers path.
Yes, exactly.
I didn't get the part about, so you said that with the C tree, we copy on the heads, right?
I think, you copy the heads.
And heads, it's not necessarily a leaf, so it might be just any nodes on the file, right?
Mhm.
So can you repeat quickly what's exactly the problem with the B tree? Because like, okay, with the B tree, we gotta come to the leaf, right?
Mhm.
And, but like, this leaf just has a pointer to the next element, this chunk, basically, and we can just copy the very first element, right, to get the whole chunk.
Mhm.
But I didn't get how this works, the C2 thing.
So-
We have to traverse for the whole.
In the B tree, first of all, exactly as you said, like you always have to traverse to the leaf to make an update. And in the functional setting, not only do you have to traverse, you have to copy every node along your path from root to leaf. And the nodes in the B tree can be big, like they have B elements and each of them has B pointers also.
Mhm.
And the pointers are like at least equal size to the elements, if not more. Like pointers are 64 bits.
Mhm.
So the size, like total size across the entire tree of copying may be large, whereas in the C tree, you only have to, at the internal nodes, you only have to copy the head.
Okay, and do we then just lose the suffix information, or we kind of like, what do we do then? If like a had suffix,
Uh-huh.
we don't care about it now, or like what's the whole suffix thing?
If you don't have to modify it,
Yeah.
like you don't need to copy it
Mhm.
in the function, in this setting. So like here, this bottom node is like this red thing is the thing that you're trying to update.
Yeah.
So you only have to copy the suffix that contains the thing that you're trying to update.
What is the update in the intermediate nodes, not leaves or?
Then you have to copy the thing up until that point and then the suffix at that point. Like you don't have to copy further down.
Either or remove or just.
Yes,
one.
it can be at any of them. But in anything that does a write, you have to do, in the functional setting, you have to do a path copy. Because you basically, you keep around like all the previous versions pretty much. Yeah, so this is like, it's like like I said, it's independent of the data structure in some sense. Like you can have a functional tree or you can have an in-place tree. Like normally almost all data structures are in place, I would say, like you just directly modify the thing. But in some cases, functional is good because then you have versions. So if you care about accessing previous versions of your data structure, or actually the main reason that they do this is if you do this versioning, you can do algorithms and updates simultaneously. Because you always have like a valid version, a valid view into the tree, no matter how many updates are going on at the same time. That make sense? Okay, so yeah, that is path copying. And I said that they have special algorithms to do batch updates. And so batch updates in a C tree are based on tree union, which is you take two C trees, C sub 1 and C sub 2, and then you output a third C tree, C, containing all the elements in the union of your two initial C trees. This is tree union. Okay, so they have 4 steps, but we'll go through them. The first step, basically at a high level, what they're going to do is you take the 2 trees, you cut one in half based on the root, and then you find like the root, say it's C sub 2 in the first one, and then you kind of like recurse on the 2 halves. Like you find the midpoint in one of the trees, you cut the second one based on that midpoint, and then you recurse on the halves that you got. That is the high level of what's going on, and then this is just the exact details of how you do it. So the first step, like I said, they have this functionality called expose, and they're going to call it on without loss of generality, C sub 2. And the input of expose is a C tree, and the output is the left subtree, the element and prefix of the root, and the right subtree. I should say suffix maybe. So yeah, so expose will give you these 2 subtrees and the root pretty much, and so this will cut it in half, more or less. And we're going to use this element that we got at the root to cut the second tree. So like I said, using the root that we got from expose, this root of C sub 2, we split the other tree C sub 1. And split is some actual API that the library implements as it takes as input a C tree and an element that you're going to split the tree on. And as output, you get 2 C trees, B sub 1 and B sub 2, where B sub 1, like the left one, contains all the element less than K, which is the element that you split it on. And the second one is like the right one. So it contains all the elements greater than the one that you split it on. So like you would get this element K, and then you would, this is your tree, and then you cut it based on the key that you got. Okay. This is a lot of details, but at a high level, you can't just recurse on these 2 halves directly because you might have some issues. Like for example, you had a tail here for the root in the first tree, and then you have some prefix in the second tree, and you might have basically the issue is that some elements in this tail might come after some heads in this tree. So you can't just directly merge like this left one with this left one, because you might miss some of these in the tail. And then vice versa, like you have a similar issue on the other side. So basically the way that they fix that is that they basically split the remainders like correctly so that you get the right elements going to the left and the right side. This is like a lot of notation, and maybe we don't have to go through it right now. And then finally, once you have the right set of things that are going to merge, so you make sure after doing the splits that everything you basically determine like a left and a right side, and you're trying to do recursive union on those halves. And the reason for this was just to make sure that you got the remainders right. Oh yeah, and of course you can do these 2 halves in parallel. So that's the whole reason that we're doing this complicated thing is that we want to parallelize within a tree. Like you can imagine that each of these things is holding one of the edge lists, and we parallelize over the edge, like over the vertices, but this is how you parallelize one level down. Yes.
we merge like L2 and D1 and R2 and
Yes,
D1.
yeah, you merge L2 and B1 with some remainder, maybe, and then you merge R2 and B2 with some remainder. Like, yeah, exactly. And you can do all, I guess this is like order one. Split is maybe also order one. It's definitely less, it's like maybe log at most. And then you recurse on the two halves. Yeah, and so like I said, each one of these C trees can be used to represent one of the edge lists. So you would replace the linked list in an adjacency list, or you replace the block linked list in Stinger with one of these. And you build a tree of trees, pretty much. Like you would use this tree one level up also for the vertex list. So basically for graph data structures, you can use any data structure as the thing to store the edge list or to store any individual edge list. Okay. So here are some performance numbers that they had. Like I said, they use union in the C trees to implement. So they implement this batch update API at the highest level. And in the batch update API, you give it an array of some size. And under the hood, they separate it out. Like you give it an array, under the hood, they separate it out into the different vertices, and then they call the lower level batch update that we just saw on each of those edge lists. And you can see that they did some experiments. The batch size increases from 10 up to about 10 to the 6. And for Stinger, I guess these are the absolute times, and these are updates per second. And Aspen is the graph streaming system that they built on top of C trees. And the updates per second are up to 71 million about in Aspen, and they stop at about 300,000 in Stinger. So this is several orders of magnitude.
And this is function.
It is functional, yes.
But I mean, isn't there more overhead to like copy and like objects and stuff?
Yes, so there is overhead to copying, like to the path copying. But
With all that,
even with all that, it's still like this, because they have this parallelism across the, they have this parallelism at the lower level. And yeah, so they evaluated batch updates, and then they also evaluate several algorithms. Here they just did two as an example. This is breadth first search, and this is betweenness centrality, which is another graph algorithm. And the graphs are here: LiveJournal, ORCID, and Twitter. These are commonly used experimental graphs. And they ran ST as Stinger. These are times. LL is Llama, which is another graph system. A is Aspen, so these are times. And these are speedups. So Stinger over Aspen, up is good. So like 10 would mean that Stinger was 10 times slower than Aspen. Well, good in some sense. Over 10.2 here means that Stinger was 10.2 times slower than Aspen on BFS run on this LiveJournal graph. And the reason that these algorithms are so much faster is because Aspen uses this, like these blocks. I think the blocks may be bigger than they are in Stinger. And also Aspen uses compression, like the same compression scheme that we talked about last time, using variable size chunks. So they have better spatial locality. You can see like this, I think in the original Stinger paper, they didn't actually report the algorithm times. At least not, I read it earlier today and they implement a bunch of algorithms, but they just didn't report the times. And I think they just ran like what was on the Stinger repo here, and then they reported the times that they got. This is not super important, so I'm going to skip it. This is just like they have a follow-up paper from Aspen, and it turns out that they can do a little better. And the way that they do it is they remove the randomization, which is not clear to me why that it was randomized in the first place, but they did remove the randomization. They did a little better. Like you can see they got about 20% at best. Questions? Yeah, I think they just cut it up into uniform blocks and then they build the same tree on top. I'm not sure why it was randomized in the first time. It's cool. Yeah, I don't know. Unclear. Questions? Okay, let's keep going then. Okay, so we just went through one, I guess technically two, but the last one was really fast. Batch parallel data structure, which was seed trees, and later on their follow-up paper is called pack trees. There's a whole bunch more batch parallel data structures, but we don't have time to go through them. They're mostly based on trees, like a lot of them are based on binary trees. Seed trees and pack trees are like the fastest tree batch parallel data structure because they are blocked. And there's also, I think, a skip list version, batch parallel skip list version, but they're all built on pointer-based data structures. So, and they're all pretty much based on tree union, or skip list union is very similar to tree union. So they all rely a lot on these pointer adjustments. And from the point insert case, like ignoring batch parallelism for a second, we know that pointer-based data structures are fast to update, even in the point update case, but slower to scan compared to PMAs or other contiguous data structures, because PMAs or dynamic arrays are contiguous, whereas pack trees or dynamic trees are not contiguous, like they're based on pointers. So you see this cartoon again. Previously, it was CSR and a GCC matrix was here, I think. But now PMA is on this side, the range queries are good, but the update is not so good. And previously PMAs don't have any batch update support. So the updates are especially poor, but the pack trees have good batch update support and the range query performance is actually good. They're not so far as this cartoon might look, but like if you put them really close in the cartoon, it doesn't really help that much. So yeah, and so recently I have been working on PMAs with batch updates. And although PMAs are asymptotically worse than trees for updates in a theoretical sense, in practice, they're way more cache friendly. And so they can actually achieve faster updates in an empirical sense. And I'll show you data. I think we talked about this when we were doing cache-friendly data structures, but we can go back through it. The packed memory array, or PMA, is a cache-oblivious ordered dictionary data structure that supports elements in one contiguous array allocation with a constant factor of empty spaces for updatability. So this is kind of what you were talking about earlier. Like, can you put the empty spaces? Turns out that yes, there's a data structure based on this idea. And the way that it works is that you have one giant allocation and you allocate theta n cells, where n is the number of items that you have, but you allocate like a constant factor of extra cells. And you distribute the cells in some way so that you can prove some bounds about it. So the PMA stores a constant factor of extra cells. And the main distinguishing feature is that you have one giant memory allocation rather than node allocations. And it's implicitly split up into chunks of size theta log n, and those are called PMA leaves. And the way it works is that like the whole thing is sorted. And in this picture, blue means that elements are there and white means that it's empty. So you always have some empty spaces in the PMA leaves. And you kind of, in some sense, you treat it implicitly like a tree. Like if you wanted to do a search, you would search on these blocks. So like I said, it maintains the spaces according to density bounds, and density bounds are how you can prove theoretical bounds about it. Density bounds just tell you max and min how full the leaves can be. And more generally, not just the leaves, but the entire allocation defines this implicit binary tree. So the leaves, like I said, are size theta log n, but the entire thing defines this binary tree. So these are the leaves, and then one level up from there, their parent is this entire region of these two. And then one level up from there, it would be all 4 of these. And then the root of this tree is all 8 of them. And the way that you maintain the thing is that you have density bounds on every single node in this tree. And at any point over time, every node, leaves, and all levels up have to respect some bounds in terms of how full they are. So you always have some guarantee about how many spaces you have at any time across the entire thing. Yeah, and density, like I said, is the ratio, it's just the ratio of filled cells to total cells. So in a normal PMA, this thing is bounded above by 1. And you maintain this implicit binary tree. Yes. This thing is not ever stored. This is just, you can generate, like you could think of this as a tree on, if you store the densities, like you could see how you would generate it, like in parallel, you would count all the cells that you have. And then you can just, once you have counted all the leaves, you can go up from there. All right. So like I said, searching in the PMA, you just do a binary search on the first element in each one of the leaves. So you would start in the middle. Here, suppose that the thing was left, so you would go left. And here again, suppose this thing is right, so you're here. This is the last level, you're already in the leaf. So you just do a forward scan of the elements inside the leaf. And the search costs, you have n over log n leaves. You are doing a binary search on all the leaves, plus log n over b, because this is how many possible cells that you have log n cells in a leaf, and over b is because you're doing contiguous scan. This is in the IO model. And so that would be log n cache misses of log n. So the PMA maintains these density bounds by redistributing after every update. And this is the steps in a regular PMA insert. There are 4 steps. So we have this PMA here. This is just 2 leaves because illustrating the rest would be too hard. Suppose that we wanted to insert 22 in this PMA. You first search for where it's going to go. So here you would find that it's supposed to go in this leaf between 19 and 89. Then you would place it there. You would put 22, and you're always guaranteed to have at least 1 space based on the density bounds. And then here the density bound is 0.9. It happens to, like in this example. And so you would count every leaf. So you count this and you see that the density is 1. And 1 is greater than 0.9. So this violates your density bound. So you have to redistribute the elements from right to left to maintain density in both. So now once you move 1 to right to left, the density becomes 0.75 in each leaf. This is 2 leaves. If this didn't have enough space to accommodate, you would have to go up 1 level in the PMA tree. And like, if that wasn't enough, you keep going up until you find something that can accommodate you. Or if you go all the way to the top and you couldn't find anything, you double the whole thing. That make sense? Right. So if you have questions, please tell me, because we're going to build on this to do the batch inserts. So for batch inserts, there's going to be 3 main steps. The first step is batch merge. So remember, in batch insert, you have a batch, which is an array, and then you have your data structure, and you want to, in parallel, merge all the elements from the batch into the data structure. The first step in the PMA is going to be batch merge. So you take all the elements in the batch, and then you merge them to the locations in the data structure that they're going to go to. These are like corresponding to the 4 steps in the point insert. But I guess here, merge and place and search are combined into merge. Then these steps are the same pretty much as in the single one, except now we have to count and we have to redistribute. So that's the same as in the point case. But because we did a lot in parallel, we may have may have many to count and we have many to redistribute potentially. And so part of the part that is hard is doing this in parallel efficiently and correctly. So for batch inserts, the first step is to do batch merge. So like I said, your goal is to merge the elements in the batch into the correct positions in the PMA. You have this initial data structure and we have this batch, and the colors are just the different leaves. And here, it happens to be nice that they are all half full, but they don't have to be. And these are the elements in the batch, and they are colored according to where they're going to go. So for example, 2, 3, 4 are going to go to this first leaf.
Do you already know the neighborhood?
No, we're going to find it. Good question. I will tell you how to find it. This is just for illustration for now, but initially you don't know the labeling. But we're going to find it. So, yeah. Okay, the first step is, this is kind of like tree union, or the high level structure of this looks a little bit like the tree union that we just saw, but of course now it's different because you have arrays. And so, like, you can think of this as tree 1 and tree 2 in some sense. So the first step is you pick the midpoint of the batch. So this is like the exposed step in the tree. And you search for the location of this midpoint in the PMA. So the midpoint in the batch is 8 in this example, and you search for where 8 is going to go. So in some sense, this is like split. You split the PMA based on the midpoint that you picked in the batch. And you might have to scooch it a little bit because 8 is not the beginning of this PMA leaf. So you have to go left, but if you do, but you know where you have to stop because you know the front of this leaf. So, okay, so you had 8, and this is just the same as search in the initial point case. You have 8, and then you search for 8 in the entire PMA. And then you find that it's going to go into this leaf. But you want to find all the elements that are going from this batch into this leaf that you found. So that's why we have to scooch it a little bit possibly. And here in this case, we move it over to 7 because that is the first element from this batch that is going into this leaf. And you can find that by like quadratic doubling. You can find that in log. If you know the start of this leaf. And so that is the lower bound for what you have to find here. Yes.
I was gonna ask, why don't we just binary search for 6 and the batch? But
You can also, yeah. I think in the actual implementation, maybe you can do like, you look a little bit linearly, like as an optimization, you probably like look a little bit to your left. And if you don't find it, you do binary search. Good question. Yeah, you can also do just a binary search of this thing into this thing. Mhm. So, and then you merge those elements, 7 and 8, into the PMA. So that's just regular array merge. It's like a 2-finger scan. And now this is basically like split for trees. Now you can recurse on the 2 halves. You have this one and this half. This is here. And then these are the elements in the batch that are not yet merged in. So once here, in this case, we happen to be at the end of the leaf, but you have to find both the start and the end points. And you can do both of those with binary search. So yeah, and then you just repeat the same process all the way down, and you can do all this in parallel, these 2 halves. And you're only ever merging into, like at each level of the recursion, you're only, any single function is merged, like any single node in the recursion is merging into only one of the PMA leaves. In some cases, we may need to merge more elements that we have than empty spaces that we have in this batch case. You would never have this in the point case, but in the batch case, sometimes you do. And since the other leaves may be happening in parallel, like your particular thread is only ever dealing with one leaf, but like the neighboring leaves may be getting merged into, so you can't overflow into them. So in that case, we just make some out of space, like out of place storage, and then keep a pointer to it in the leaves. And this is again, like a little different from the tree case, because you never have to do this in the tree. You're basically, in the tree case, you're basically like rebuilding the thing from the ground up from the array in some sense.
Is there a reason why we're pulling the whole merge leaf? Like,
In the out of place, like why don't you store some of it here and some of it out there? You could, yeah. I think it's just easier because then you don't have to like deal with finding the end of this and then go to here. Like eventually you're gonna have to put these back in.
yeah,
And I think it's not a theoretical thing. I think it's just easier. Yeah. So here we just keep the count and the pointer to the end.
it'll be a fine.
Here 5 is the count. Yeah. So yeah. So this was just like we didn't have enough space and we had had to put some out of it. So like here, we only had 2 empty spaces and then we had 3 elements. So that's why these are all here.
Then why do we keep the one there?
Why do you keep the 1 there? I think that's typo. I think it should be just 5 in the front, because you no longer need the heads in the next step. I think, because the next step, like after you do all the merges, then you are doing count and redistribute. And you don't need the heads to do either count or redistribute. You just need the total volume. Yeah. And just like in the tree case, like I said, batch updates can save you work because you only have to do 1 search per PMA leaf that elements are destined for. Like all the elements in that particular part of the batch that were going to the leaf, you only have to do 1 search for them. Whereas if you're going to add them all in serial or even concurrently, each one of them would have to do the same search. And this is just, again, the same idea, like you have a batch merge. Here's your out of place. Oh, you have to store like a special thing telling you that this is out of place. Like, so rather than 1, I think it should have been like some, I don't know, maxint or something to signify that this thing is not like a normal PMA leaf. And then, yeah, so then somehow you have to figure out that this is too full and this has enough space, and then you redistribute. Do you see that? Like if you knew all the counts, like after this merge, if you knew how many elements were in each leaf, does it make sense that you can easily redistribute them? Yes, like if you have to go up 1. Yeah. So basically, like to do the redistribute, you have to look at every leaf that got touched, and if it is exceeding the density band, you have to go up 1 level. You can do like tree sum, exactly, if you have the counts. So the hard part in this is actually finding the counts, because once you have the counts, like you can trivially do the redistribution in parallel.
How does we decide which neighbor sends the overflow?
The PMA, like the implicit tree determines the redistribution, like which neighbors you're allowed to redistribute into. Like the whole thing determines, like the contiguous blocks build an implicit tree. And you can only distribute with things, either your neighbor or your ancestor in the tree.
The one leaf only has 1 neighbor.
Every leaf only has 1 neighbor. But every internal node may have more than 1 child. Like if your neighbor doesn't have enough space, you have to go to the neighborhood of 4 around you. In the binary tree case. Good. Yeah. So like I said, the main hard part is counting. And it actually turns out that this is the hard part, because if you trivially do them in parallel, it's actually not work efficient. And the issue is that this isn't, like this is your PMA, and the dots are elements in the PMA, and pink means things that were modified in your batch merge. And these are the counts. So like here, there are 2 elements, here there are 8 elements, and these are the density bounds. So this is the maximum number of elements per nodes. And the way you determine how to do the rebalancing is here, like 2 is not exceeding 6, but 8 is exceeding 6. So you have to go up 1 level in the tree, and then you see that this entire thing, if this entire thing can accommodate the next level density band. And then if so, you can do the redistribution such that it respects every lower density bound. And the problem, yeah. So this is how you do the counting. And if you had a good serial algorithm, you would only need to count every cell that was, yeah, like you have some lower bound on the number of cells that could possibly need to be counted. And you want to count only those cells to achieve the lower bound. And so an efficient serial algorithm would cache the counts. And so you would avoid, even if you had to go to the ancestors, you would look at the cache count first. And if you had ever counted a cell already, you would look at the cached count, and then you would never recount the actual cells. that make sense? And so the issue with this is that like this caching, it can happen if you do them any order in serial, but if you do them in parallel, you're not guaranteed to have counted what you needed to in advance. Like you may recount certain regions. And you can come up with theoretical cases in which you overcount by some non-constant factor. Why can you overcount? So for example, like here, in this example, we had to go up the tree several levels because many nodes had, like this one violated density bound. And when you go up one level, this one continues to violate this density bound. And so you have to keep going up here. And so but in parallel, if you are also counting this one, like suppose you're counting them concurrently, you would count this one. Well, here this doesn't violate the density bound, but suppose that this one did, then you would have to also keep going up. And but you would have counted this one along the way when you're going up to here. Like when you counting a node basically means counting all of its children. And so if two children are going up to the same node and you're counting all the children in parallel, then they are going to count the same subregion. Yeah, good question. That makes sense? Yeah, it's a little complicated. So yeah, so basically the issue is that like some regions may overlap, and then if you have too many of them, you can actually prove that is super linear. Yeah, I will skip it for now, but in the paper, there is a work efficient counting algorithm. Basically, the way it works is that it goes level by level to count the nodes. Like you go from the leaves and you go one level up from there, and you always save what you counted before. So when you go up the levels, sometimes you're doing like a top-down search or a top-down traversal, and then you're always guaranteed to never recount any cell that you have already counted because you just save your result.
Something to be work efficient.
Work efficient means it does no more than a constant factor of work than the best serial algorithm for the problem.
Okay.
Yes. All right. There's data. This is batch inserts. Up is good. This is inserts per second. Blue is the serial one. Red is the parallel one. And the x-axis is batch size. You can see that the serial one, even on one thread, you get 2.5x speed up because, like I said, you can share the work from searches, and you can do the batch merge, which is more efficient than doing single point merges. And the parallel case actually looks pretty good. You get 47x speed up over this point, but it is not ideal because you only get 20x parallel speed up. This is on 128 threads, and that is because the entire thing is memory bound. So we also did some compression like they did in C-trees. And the compression is just exactly the same as what I said before, like those k-bit chunks. And then you can see that the scaling actually does improve. Like red is compressed, blue is uncompressed, and Y is speed up, parallel speed up on threads, and X is cores. And the high level is that like the blue stops scaling because of memory bandwidth.
Oh, what's 64H?
64 hyperthreads. Oh, the left one is batch inserts. The right one is range queries. Range queries are just like give me all elements between X and Y. So it's like a search plus a scan. Yeah. The compression also improves the throughput. This is just throughput. Red is compressed. It's a little bit higher. I'm gonna skip this. I want to go back to representing it, going back to graph representations for a second. So the way that you use this PMA thing to store the graphs, of course, you can use one per node. In the compressed case, you can also use one to store the entire thing. So, I mean, you can also do this in the uncompressed case, but it would waste a lot of space. And the way that you save a lot of space in the compressed one is basically assuming that you have 32-bit edges. You store each edge, or sorry, you have 32-bit vertices. So each edge is like 64 bits, because they're just two vertices next to each other. And you just store the entire edge list in sorted order. And when you use delta compression, you often, so here like the edges are UV, UW, UX, and delta compression subtracts the elements from each other. So you do UW minus UV, and here you would just elide out the upper bits. Yeah. Results. This is the y-axis, this is the x-axis, these are algorithms, these are batch inserts. The high-level idea is that the PMA is, on average, slightly better on algorithms and also better on inserts because of the cache optimization. Yeah, to wrap up, dynamic graph data structures or containers, you need to support both efficient algorithms and updates, and there's tension between algorithms and updates. So a lot of the data structure design is in overcoming the trade-off. Outside of just performance, graph data structures may have other important features that people care about, like versioning or crash safety or other stuff. And in addition to the few that we did today, there have been, like I said, 20+ years of papers in this area of all kinds. These are in memory, but there's like transactional ones, there's concurrent ones. You can do distributed and GPU. Thank you. That's all I had.